could be. And I understand my so, with that introduction, I give you Todd Lee, mathematician extraordinaire.
Okay, so my wife is in Maine in the middle of a blizzard. So I told her I would stream, but I'm also doing screencast-o-matic just in case. So that's why my picture's down there. I'm not that. Anyway, okay, so I would like to thank all the sciencey types to invite a mathematician at all, because I'm not a scientist. I know that. And as a matter of fact, mathematicians don't get invited often even to math talks because we're mathematicians. But what I'm going to do today is something that all of you can participate in, because I am not going to be doing some crazy mathematics. I am going to be doing arithmetic. I am going to be doing arithmetic. I was thinking about my boss, Kelly, and I said, what would Kelly like to see? And I was like, well, I better keep it at arithmetic. And so here we go, all right? So the first thing I'm going to do is, this talk's not really about pi. This is about a neat trick of approximations that does have a lot of use back in the day when we didn't have universal gears and we actually had to count the number of teeth on gears, and I'm sure people still do that. But 3 seems to be, pi should have been 3. Now let me explain that. If I take a line that's 1 unit long, that black line there is 1 unit long, and let me move my cursor. This is all in mathematics. If I take, hold it. My wife said stop it. All right, there. I stopped it. Nope, no I didn't. Yeah, I did. Sorry. Technology, I know nothing about technology, sorry. All right, so if you take a line and draw a 1 unit line, and then you start, oh my goodness. Ah, good. And if you draw a circle with that line as its diameter, and you drew the distance of that unit length 3 times, that's how far around you would get. Make sense? So the red arc, the green arc, and the blue arc are each 1 unit. They're all the same length as that black line. And you notice it's almost all the way around, but not quite. To get all the way around, you've got to go pi times. That makes sense? So that's what pi is. Now, most people know, and I've run into more than my happy share of students who, and other people, not just students, who would like to think that pi is 22/7. But quite frankly, they're so close that I don't give them too much grief. Now in this picture here, I put 3 and a 7th. So 22/7 is 3 and 1/7. And if you'll look way over here, I know I'm supposed to use the fancy laser, but I like pointing. If you look at this right here, that's the 1/7, and look how close it comes. That looks like it ought to be pi. However, what I'm going to do is I'm going to blow up on this part right here. I mean, I don't mean like blow up on the screen, but just zoom in right here to about 1/1000th of the measurement. And let me explain what you're looking at here. So here's the 1/7 part coming in. There's the line that's the diameter. Here's the beginning, starting right there, going down is the red arc. And you may not even be able to see it. You see that little black line? That's 1/1000th of the unit of the diameter. And if you'll notice, there's a little, you'd have to get up here with me. Come on all up here. I'm sure. There's just a little piece of orange there that's the overlap. 22/7 is ever too much to be pi. Now what I want to talk to you is there some way, I mean, you could have just fooled around until you ran into 22/7, but it turns out that hidden behind 22/7, there's a very clever way of thinking about numbers, arithmetic-wise, thinking about numbers, that I think this is I take every opportunity to introduce to people. And if you want to email me later and get some Google search things to throw at you, just email tlee, and you've got me, at elon.edu, TLEE. All right, let's go on. So let me just point out that, so there's pi out to a bunch of digits, not too impressive, but there it is. And there's 3 1/7. And it's got the first 3 digits right, but it's only off by about 1,000th on the next digit. And so 3 has a relative error of 4.5%, but 3 1/7 has a relative error of about 0.04%. That's pretty good. It won't get you to the moon, but it's pretty good. All right? So let's go on. Yeah, you don't want to use. So what I want to talk about is how to shove, and actually I want to get down to nudging. All right? I read a book called Nudging just recently, so we're going to talk about nudging a fraction, but first we're going to talk about shoving it. So I want to make sure that everyone is following along. Now this is coming right out of grade school, okay? You can be right. So say it kind of softly until your neighbor agrees, and you can say it loud enough where you won't have to embarrass yourself. So here's what we're going to do. Here's my question. If I take the 5 in this fraction and I increase it, I shove it to be something bigger, I want you to turn to your neighbor, your math buddy for the night, and tell them what's going to happen to the fraction. Does the fraction going to get bigger or is it going to get smaller? Tell your math buddy, don't tell me. Now you got a 50-50 shot here. If you don't get this right, the rest of the talk is going to hurt a little. All right. Are you ready? I heard it a lot, so I want to talk about it. If you shove the 5 into being a bigger number, then the whole thing gets smaller. Now that is grade school, right? We can hang with that. And that's a powerful notion. So I'm just going to point out that we could shove it by 24, because that's what I want you to think about, is adding a little something or a lot of something. So if we shove it by 24, we get 4/9, and that's less. We can shove it more. But no matter how much we shove the bottom, talk to your math buddy, what number can we not get to? There's a lower bound to this. If we kept shoving it, what's the lowest this number can get? Talk to your math buddy. I don't hear you talking. Now this is a little bit harder, but I heard it, so I'm going to go on. No matter how big you make that bottom, the whole thing stays positive, and you can make it as small as you want. Just think about shoving it to 1 trillion. Now you've got something that's almost 0, right? But it's not quite 0. That's all what I want you to recognize. There's a lower bound to this whole thing. That's what we call that. All right, good. Now, I don't want to shove fractions. There are certain laws that will disallow that. Well, what I would like to do is talk about nudging a fraction, okay? So you were taught in grade school that this thing down here at the bottom, that you should immediately do something. You were given that and you were told to immediately get rid of it, that you needed a proper fraction, one that wore a suit and tie and went to work and da-da-da, right? You can't have this business of a number on top of a number plus a number on top of a number, but actually I'm giving you permission. We want very improper mixed fractions, all right? And it's the only way to go. So if you'll look down here, I told a lie. Now, see here, yeah. What? Now look, I know that's bad. I'm not good at counting, all right? Give me a break, give me a break. Look, but I'm the only person you know that can run the Mathematica and make it right immediately. There you go, right? The boy's got skills. The boy's got skills. All right, here we go. Now, we shove it by 1/8. I know you like decimals, but we're going to try to get out of the decimal game, because it turns out that by increasing a decimal, no matter what your base is, you're increasing by a power of that base. Now, if you don't know what I'm talking about, that's fine. I'm just saying that every time you try to get closer and closer decimal-wise, you're going 10, 100, 1,000. We want to go baseless. And to do that, you need to follow me down this nudging train, okay? So what I'd like you to talk to your math buddy now about is, you see this 4/5, and we've nudged it by just a little bit, 1/8. Tell me where up here does that number fit in? Is it going to be on the other side of 4/5? Is it going to be closer to 0 than all those other numbers? Where does it fit in? Talk to your math buddy. You think you got it? So to think about it, the more that we shoved the bottom, the more it moved smaller and smaller. So if we just nudge the bottom, it moves to the left. It gets smaller, but only by a little bit. So what it's going to do, it's going to land right in there. Right? Did you get that? We're following? Oh, then I've got you. I'm going to show you something great. If you can just follow that, well, that's not true. There's a few other things, but we'll get to that, okay? So that's called nudging. Now, I want to go a little bit further. Now, if I took 5, and instead of having 5 on the bottom, I put 4 on the bottom and then nudged it to be a little bit bigger, do you see what happens to it? I've got 4/5. I take 4 over 4 plus a little. Where is that going to end up? Talk to your math buddy. You can just lean over and say, I think it's left or right. Right? Right? You don't have to say it so loud I hear it. That's okay. All right. So we're just zigzagging a little bit. Now I just want to make sure you're following. Kelly, are we following? Oh my gosh. This is the first time I've had at least one person follow me after 10 minutes of talking ever. So I win. Okay, so what happens there is that we've actually taken away from 5. A good amount, about 9/10 we've taken away from 5. So we made the bottom smaller, and so the whole thing got bigger. So we can nudge in both directions, though that was almost a shove. Okay. Now we're going to talk about a mini nudge. Okay? And yes, I have micro nudges and nano nudges, so I thought that's about the closest I can get to science as we're going to get here, okay? So what I want you to think about is that means shoving 8 to something bigger. If I make 8 something bigger, what happens? Just think in your mind. You don't even have to tell your buddy, because your buddy doesn't know what they're doing. It's all right. If I shove, now you just stare at that and see if you can get that. If I shove 8 to be bigger, something bigger, then 1 over 8 becomes smaller. And then 5 plus that smaller thing is smaller than what it was. So what happens to the whole fraction if the whole bottom gets smaller? You following? Look, don't worry if you're thinking, why in the world do I care? Don't. It's coming. I promise you. There's some beautiful, beautiful mathematics coming down the pipe, or at least I guarantee it is. You may not think so. So anyway, so that means that we have to kind of follow this zigzag trail up. If that 8 gets bigger, then the 5 plus 1 over 8 gets smaller, then the whole fraction gets bigger. Mini shove. Okay, so that means that, notice if I got 5 in the 8th and 5 in the 1/9 where that will fall, because the 9 is bigger, so the whole thing ends up getting bigger. Now I'm going to do even a smaller nudge, sorry, no more shoving, nudging, a micro nudge. Let's check this out. So this is the kind of thing I want to think about. All right, so these are tiered fractions, and I know you were told never to let this happen on your test, but I'm telling you that something beautiful happened. You were told not to allow this to happen because of the beautiful thing that could happen. You could fall in love with mathematics, and then we'd have a room of mathematicians, and the math people don't want that because we need a job. So that's why you were told never to look at these. All right, I'm saying it free. I'm free. I'm tenured. I can say the truth. Here it is. All right, so you see that we've got tiers of these things, and you see how they're following in there. So let's play another one of these nudge games. Okay, so follow along in your mind. The next step I'm going to look at is the 8 plus. So if the 3 gets bigger, what happens? The 8 plus 1 over 3rd does what? Right? If the 3 gets big, Kelly, you following? Okay. The 3 gets bigger, the 1 over 3 gets smaller, the 8 plus 1 over 3 gets smaller. So what does 5 plus 1 over that do? All right, I heard it. Someone's feeling brave. They're like, get larger. I got it. Yes, get larger. And if the bottom gets larger, the whole thing gets smaller. Oh, I love it. Isn't it nice? You're all wrong. No, that's right. That's right. It's good. Sorry, I'm required to do that every now and then as a mathematician. So, look at what's happening here. So, I'm building up this technique for nudging and micro-nudging, mini-nudging my way in between other numbers. And I'm going to use this technique. Let's see if I do. Yeah, don't look at that. You're not supposed to have seen that. Okay, so what if I do it the other way? What if instead of making the 3 bigger, I make the 3 smaller? Then this back and forth occurs, and I end up with a number that gets bigger. Make sense? I didn't realize that talking to people eating makes me very hungry. It's okay. I'm not really hungry, I'm kidding. So, we get this game where I can actually zig and zag in any direction I want, and that's the trick that I want to use. All right? I'm getting ready to do graphics, so just hang in there. I know people are like, all these numbers. I want to show you one more trick, because what I want is to get something even more special. What I want is only fractions that have 1 on top, and I'm going to show you that we can pull that off even with fractions that don't have a 1 on top. I can, again, undo what you were told to do in grade school. So 4/5 I can flip and write as 1 over 5/4. Do you believe that? If you don't, remember the days when you were given 1 over 5/4 and you were told, flip and multiply. All right? Which is not very polite to say, but still. And then 5/4, when you take a fraction that's smaller than 1 and you flip it, it becomes bigger than 1, and you can take out that integer, and we get this 1 sitting there. Now, I might have to do that a few times, a few different levels until I get nothing but 1s on the top. But the claim I'm making, you're going to have to allow me several different claims. The claim I'm making is that I can always work it so that given any fraction, I can actually nudge it back and forth till all the fractions have 1 on top. Because we like things that are nice and normalized. Very unlike life. Okay. So this is the theorems. You've got to have theorems in the math talk. They take our license away if we do not state theorems. But I want to talk about continued fractions. If you want to go off and study this on your own, science and math, and I imagine other areas, has gotten so wonderful on YouTube because you name any subject, and there's 2 or 3 people who have done amazing talks on those subjects. And I love it. I love it. And I watch them all the time, too much. So you can go on YouTube and watch continued fraction, but I don't think you're going to see this nudging approach quite like this. But there's a lot of other search words, and again, just email me and I'll send you some more search words for that. But here's what I got. I want to consider a number where A, B, C, and D are positive integers, meaning 1 or 2 or 3 or 4 or 5 or 6, something like that. And I want to think about all the numbers where I got a counting number plus 1 over a counting number plus 1 over a counting number plus 1 over blah, 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 all the way down. It might stop, it might not stop. It might not stop. Okay, here's what I want you to know. Every rational number, that was the numbers you started with in grade school, all the fractions and stuff, every one of them can be written as uniquely in that form, where it stops. At some point, it stops, finite. And there's only one way, none of that 0.9999 equals 1 business. That's gone. You remember that? That 0.9, Kelly, do you remember that? The 0.9999 forever is equal to 1? You lie. How can you lie to me? You're my boss. Don't do that. Oh. Okay, every algebraic irrational number, like square root of 2, 5 plus cube root of 8, things like, well, that's 2, cube root of 13, all of those numbers have an infinite extension, so the fraction goes on forever, but it's repeating. So now the algebraic numbers look like the repeating rational numbers. So the rational numbers have a finite fraction, the algebraic numbers have a repeating. Cool. Every real number, even transcendental, there's a lot more real numbers than there are just square roots and stuff. All of them have a unique representation in this form. That's cool. All right, that means that pi has one too. As a matter of fact, some of them are really cool, and this lets you know that e, the Euler number, is far more important than pi because it actually has a pattern to its continued fraction, where pi doesn't. And if you truncate, that means chop it off, cut it off, one of these continued fractions for a real number at any point, at that point you will have in some sense, no, in all senses, the best approximation for that number for the size of the denominator. Meaning that any number that has a denominator that's smaller is further away than the number you've got in hand. 22/7 is one of those numbers we're going to find out. That if you try to use 7, 6, 5, 4, 3, 2, or 1 as a denominator, you cannot get closer than 22/7 to pi. And that will come up here, and we're going to play the game now. All right? We're going to go hunting for pi. So here's what we're going to do. So here's my picture. Now, I'm assuming that we've got pi in hand. Can everybody see that? Because if you can't, there's nothing I can do about it. I just want to know if I'm talking to myself. So that red dot right there is pi. We'll assume we've got that. It's pi sitting right there, a little bit bigger than 3. If you've never seen pi before, take your pictures. There it is. All right? And it's sitting there on the number line. Now, I'm going to start with the denominator of 1 and ask myself, of the ones that have a denominator of 1, so 0 over 1, 1 over 1, 2 over 1, 3 over 1, 4 over 1, which one is the closest to pi? Well, can you see? If you don't say 3 over 1, you're going to be lost the rest of the way, okay? So if your math buddy's got their mouth open, close it for them and say, yeah, it's 3. Look, it's closest to the red one. Right there it is. Right there. Just say 3. Okay, so 3 is close. So what I'm going to do, and I even show it to you. Look, it's blue. It's there. Now, give yourself a chance to absorb this picture. I've zoomed in I am between 3 and 4. You see that on the endpoints? On the number line, between 3 and 4. The red dot is still pi. Got that? We shouldn't be lost on that. Now here's what I want to do. I want to think about taking 3 and nudging it. Either by 1 over 2, by 1 over 3, by 1 over 4. So I show you 3 and a half. 3 and a third, 3 and a fourth, and see I'm getting closer to pi? It looks like at 3 and a quarter, I'm already closer to pi than 3 was. But I'm going to keep going until something happens. So let's keep going with this. You following? Kelly, are you following? Thank you. Kelly's like, I cannot believe I came to a math talk. All right, so look what I've done. I've zoomed in. So now look at the left hand. I'm still at 3 on the left. On the right is 3 and a quarter, 3 and 1/4. There's 3 and 1/5, 3 and 1/6, 3 and 1/7, and 3 and 1/8. So in my 3 and 1/8, I've gone past pi, but it's still a better approximation than 3. So 3 and 1/8 would be a better approximation than 3 would be. But you can just look and see which one is the better approximation there of these nudges. Which one's the better approximation? 3 and a 7th. So for the best bang of my buck, 3 plus a 1 over a number, the best I can do is 1/7. So let's take a look at that. Now I've zoomed in again. Look on the right-hand side. That's 3 and 1/7. That's 22/7. That's the thing that everybody uses to approximate pi. The red dot is pi. I haven't switched that up on you. And look down here. That's the number that's past that, 3 and 1/8. Now the trick is you see how much closer 3 and 1/7 is to 3 and 1/8. So what I want to do is to start nudging my way back towards pi. Now how do I do that? Well, if I look at 3 plus 1 over 7 plus a half, now just think about that. So I'm adding a half to 7. So I make 7 bigger. So I make 1 over 7 smaller, right? So I make 3 plus 1 over 7 smaller. So by taking that 7 over here, by taking this 7 right here, and adding a half to it, I make it smaller. And I make it way smaller by adding a half. So now here's what I want you to talk to your math buddy about. Say, math buddy, hang in there. He's almost done, and then we can get back to our meal. Talk to him about what would you do next? You see that this thing I've created here, 3 plus 1 over 7 plus a half, it is not as good as just 3 plus 1 over 7. But I want to try to get closer to pi. What would you do? Talk to your math buddy. Okay, here's what I hope you said. I hope you said, well, look, I nudged it by half. When I nudged 7 by half, I shoved it way on past down. So I shouldn't nudge it so much. So instead of nudging it by a half, I should try nudging it by how much? A third. And that's what I'm going to do. I'm going to keep nudging it by less and less until I do better than 3 plus 1 over 7. So let's nudge away. You see all those green dots? So there's 3, and there's a nudge by 1/3. The next dot is a nudge by 1/4, and then a nudge by 1/5, 1/6, 1/7, 1/8, and then they just start piling up. Now, those of you who've had calculus who think this is converging, it's not. If you nudge less and less, it will converge back to 3.17. I stopped it in time. So the question is at what point, 1 over what, do we stop the nudging? So I'm going to zoom in some more. Now I've zoomed in some more. So take note of what the 2 endpoints are. That endpoint is 3 plus 1/7. You remember a second ago, it looked very, very close to pi, but now it's not, because we've got something much closer. Down on this end is that 3 plus 1 over 7, where the 7's been nudged by 1/15. You see the green dot that's been nudged by 1 over 17? So where in the world is the nudge for 1 over 16? It is so close to pi that the graphics are fooling us here. It's behind that red dot. You thought 3 plus 1 over 7 was good. You should tell your friends 3 plus 1 over 7 nudged by 1 over 16 is the bomb. All right? Right there. The bomb. So that's what we want. That's a much better approximation. But wait, there's more. So if I zoom in where there's 3 plus 1 over 7 plus 1 over 15, and there's 3 plus 1 over 7 plus 1 over 16, and there's 15 nudged by half. Now, notice it's 15 I'm nudging because we're down another tier. So the nudging actually goes... Did I make a mistake? Oh, I thought I did. Anyway, look how close pi is, even though... That's good. That means we might have a winner as far as not equal to pi. Don't say that. But we might have something really, really good, and it turns out it is particularly good approximation. Okay? So it turns out that if we look at 3 plus 1 over 7 plus 1 over 16, this truncated continued fraction, it's equal to 355 over 113. Now, 113 is a much bigger denominator than 7. But look at this. Look how many decimal places we get for that. We're down to what? The 10, 100,000, 10,000, 100,000, million, 10 million? That's pretty good. I don't think... that's still probably not a good enough approximation to do like Mars trips. I don't know. I'll ask my physicist. Is that a good enough? Or do you have to go further? He doesn't. So, yes, that's good enough to do Mars trips. No, I don't think it is. I don't think. Why do that when you've got all of the digits? Not all of them. You do not have all of them. Okay. Yeah. Now, I'm all done, except I'm going to show you, that was the theory of the nudging. We could have kept nudging, but I'm going to stop there because I'm going to show you, one, a real easy way to do this that doesn't require pictures. But the technique is not interesting at all unless you know why you're doing it, right? And it goes fast, and it also allows us to find the next approximation like an instant, and we'll see why we may not want it. So here's the trick. Write out pi, 3 plus some decimals, right? Subtract, flip, and repeat. So subtract 3 from both sides, and then flip both sides. So if I subtract 3 from both sides, on the left I'll have pi minus 3, on the right I'll have 0.1415, dot, 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 right? But when I flip that decimal on the right, it gets bigger than 1 now, doesn't it? So when I flip 1 over pi minus 3, I get 7.06251. I separated it out, but it turns out if you take pi, subtract 3, and flip it, you get 7 and something. Now guess what I'm going to do? I'm going to subtract the 7. Now, this is an interesting thing to think about. If you like thinking about numbers and stuff, I really debated showing you some things as why this works, but I think it intuitively has some sense as to why this trick is working, and it's worth thinking about. And I wanted to leave you a little something to think about, so subtract the 7 and flip. Just do it careful, don't hurt yourself, okay? Now look at that. When we're at this point, by the way, if you took that left-hand side and reduced it to a single fraction, you'd get 22/7. Well, I shouldn't say that. Right now, we've got to the point, we've got the information for the 22/7 on the left-hand side. But on the right-hand side, it's almost 16. See how close to 16 it is? That's why things got so nice for that 1 over 16. So I'm going to subtract the 15 and do another flip. I'm going to do it again, and then I'm going to stop here. So the next term, notice we've been dealing with numbers like 1, 15, 7, 3. Suddenly we get 292. Okay? I'm going to stop here because this is one of those convenient, this is a place where the universe tells you, psst, you might want to stop because something really big is happening here. So here's what I'm going to do. I'm going to say, look, I want an approximation, so 292 and some change. I'm going to call that approximately 293, and then I'm going to unravel all of this and see what pi is approximately equal to. Let me say that again. I'm going to call this 293, and then solve for pi and see what we get. So check it out, the magic. So there's 293, and all I'm doing is flipping and adding. Okay? Now, where's the 16, you might say? Curses, you have failed me. I would never fail you, Kelly. Don't worry about it. Here it comes. Look at what's in the parentheses. You see what happened? 1 over 293, that's small compared to these 1 over. We've been nudging like 1 over 5. 1 over 15 was a pretty hard nudge. But 1 over 293 is unprecedented compared to all the others. So now, last time, tell your math buddy how good they've done, and then to ask them, that thing that's in parentheses is approximately what? No. First tell your math buddy, thank you. Always say thank you, math buddy. Thank you for doing math with me. It was a joyous moment, and we have eaten, and you've shared everything now. There's not much else you can do with another person after you've done math with them. So now tell them what that 1 over 1 plus 1 over 293 is basically. It's 1. And look what happens when we say, okay, one last approximation, let's call that 1. Oops, I went too far there. Well, if that whole thing's 1, that becomes a 1 over 16. So it's at that 1 over 293 business where we get something. Yes, you can keep going with this, but I promise you that it's not worth it. You really have to go, and now I'm going to show you why it's not worth it, okay? So I'm going to keep the 293 and compute that fraction, and I'm going to take away the 293 and compute that fraction, okay? So these are the two next best approximations. So there's 3, and then there's 22/7, and there's 355 over 113, and then if you keep the 293, can you see? You don't want to miss that part. It's the best part. You sit here this whole time and then miss this? Come on, right? that last part right there, you go from 113 to 33,000. Now you don't go around using that as approximation. You can if you're a computer, but if you've got a computer, you use something much different. You play a different game. But just on the top of your head, if you want something a little bit better than 22/7, if you want to walk down the street and feel like you're a little closer to pi than everybody else, you want to use 355 over 113. But you do not want to use that next number, and all it gets you is 3 more decimal places. It's not worth it. So that's how we can do approximations. This is called continued fractions. There's whole theories. There's cheap $5 Dover books written on it that will just blow you away and keep you busy for years. Gears are done using something called Stern-Brokaw trees that uses this. It turns out that you can learn how to add fractions by adding the top and adding the bottoms and get these same approximations. You've got a thing called Ford circles. And it turns out you've got circles tangent to other circles, tangent to a line. You can get these same approximations. This thing comes up so many different places in this beautiful stuff. And I am so thankful that you as scientists were willing to share a little time with the mathematicians. So thank you and good night. Does anybody have a question, or did I just nail it?
What does a nudge represent?
Yeah, so nudge is, I read a book called Nudge, and so I just called it nudge. That's not a technical term.
Yeah, so what it mean, like, is it force, speed, distance?
No, there's no science involved to it. Yeah, I totally agree that a nudge has kind of a physical metaphor to it, but all I meant was by a nudge is 1 over a number.
Okay, all right.
But look, it turns out the way we learn.
It's missing space, you know, like if you build space, like, so is it fulfilled by force, distance, speed, like?
None of it. When I say nudge, here's what I will say, that when I talk about nudge in the mathematical sense, I use the word nudge, and we do this all the time because I am triggering in you all these physical concepts. If it wasn't without these physical concepts, almost none of these words would make sense. So I use the word nudge because you do think a nudge to the left, nudge to the right, but there is no application to actual physics here. I promise.
That's the only question I had.
Okay. Yes, so it's all bonus. Anything else? Yes, sir.
Where can I buy the t-shirt?
Oh, this is shirtwoot.com. Shirt, WOOT.com. It's my favorite of my mini pie shirts. So if you didn't get to see it, there's a certain, it's got some, what do you call it, dark humor? Yeah. But it's a cute fox, so it's not that dark, right? It's a hungry fox. And I'm sure those are marshmallows sticking out of its mouth. I'm sure. Anything else? Yes, sir.
How many different ways are there to calculate pi?
Oh.
Can you repeat the question?
Yeah, so the question was, how many different ways do we have of computing pi? We have lots of clever ways. We've had for hundreds of years lots of clever ways of computing pi. But computing pi intelligently, to get those really big decimal places, there's probably just 1 or 2. But Ramanujan, I think, came up with the most interesting ones. There's some breathtakingly beautiful identities between things, and that's what this talk, that was my choice, is either do a continued fraction talk or do a talk about some of these series that add up to pi. And they're just absolutely beautiful, like 1 over the square of odd numbers and things like that. But the techniques that we use to actually compute pi, well, after we get so big, we have to be very clever about it, and there's 1 or 2 good ways, really good ways. And what does good mean? After a bit of calculation, you've got a lot of decimal places. This is not one of them, it turns out. Because if you'll notice, this one kind of assumes you know what pi is to start with. Right? So this is not a technique for that. Yeah. Good question. So you call it what my other talk might have been. So maybe next year I'll do that one if I'm invited back. It's not arithmetic, it's a little more than arithmetic. Yes, sir? So tomorrow is Pi Day. And I will even, to give a deeper hint to it, 2015 was Super Pi Day because if you look at the dates, it's 0314, so it's March 14th, 15. But March 14th is Pi Day simply because it's 0314. Now I will tell you two facts about Pi Day that's got nothing to do with Pi Day. One fact is it's also Einstein's birthday. So if you don't want to celebrate Pi, for goodness sake, celebrating Einstein's birthday seems like a good thing to do. But here's another thing. It turns out my wife is a professor in math education at State. We had a child who's sitting right there named Jonah, and we have another child named Delta. You can imagine how much she loves that name. But we have a child named Jonah who was born on Christmas Eve. Well, that's pretty heavy competition for a birthday, right? So we decided to officially make his, well, not officially like in paperwork, but we celebrate his birthday not on Christmas Eve, but on Pi Day. So his birthday is tomorrow by proclamation. So happy birthday, son. He's going to be like, Dad. Is that what you were looking for? There's nothing official about it. I would love someone to officially say, let's celebrate a number. We got a lot of numbers to celebrate, though. Anything else? Thank you very much.